In the previous video, we talked about control chart as being used to identify special causes of variations. Control charts are simply run charts with two additional horizontal lines, which are the control limits. The control limits are chosen statistically to provide a high probability that points will fall between these limits if the process is unstable in control. Points that fall outside of the control limit or have a pattern are going to indicate that the process is out of control and a correction action needs to be taken. The construction of the control charts assures that we know the mean and the standard deviation of the process. However, to obtain these values, we need to measure all possible process outcomes, which can be very expensive and infeasible. Instead, we rely on inferential statistics and estimates the mean and variation of the process based on a series of samples that are taken over time. This is the foundation of control charts. Therefore, it's also called statistical process control, but no worries, we will not do a lot of statistics in this course. Think about a company that is manufacturing matches. Would it be possible to measure each match, how much time it takes from striking of the box until the match is lit? Obviously, this is unfeasible, as we will end up with no matches to sell. Or think about measuring the time the customer waits at the cash register. You can imagine the burden in terms of cost, productivity, and morale if the wait time of each and every customer is tracked and recorded. We probably will need to hire a few people or invest in technology that can track and record all wait times without interfering with the process. Luckily, we can rely on inferential statistics and estimate the mean and variation of the process based on a series of samples that are taken over time. This is the foundation of control charts. Tutorial 4 walks you through the demonstration and illustration of sampling distributions, which will help you better understand how sampling works, how often to take a sample, etc. Process control analysis typically relies on two control charts: the mean chart, which shows the process average, and the range chart, which shows the dispersion of the process. Together, they indicate whether a process is in control. They should always be used together because they provide different information about the stability of the process. We will focus on control charts for variable data, which depicts how the process behaves over time with respect to a measure that is on a continuous scale, like a cycle time, wait time, length, weight, cost, etc. There are three types of variable control charts which differ by the way variation in the process is evaluated. We will use the X bar R chart to demonstrate how control charts are constructed and used. Let's assume that every half an hour, we sample the sugar content of the sauce that is produced on a particular machine, and that every time we take 5 samples. So again, every half an hour, we take a sample of 5 jars of the sauce that we're producing. The data you see here shows a series of more than 20 samples that were taken every half an hour throughout the day. Each row represents 5 measures that were taken at that time and recorded as M1, M2, all the way through M5. Using a software like JUMP or Minitab, we can get the respective control charts in just a few clicks. The visuals show 2 charts. The top chart is called the X-bar chart and provides information on how the means behave over time. Let's look at an example at the second sample. So was the first hour, first half hour, second half hour, that's when we're taking the 5 measures. And it was measured as 22.11, 21.45, 21.63, 24.34, and 23.37 grams of sugar that were in the sauce. If we take the average of these samples, we get an average of 22.58. And this value is recorded on the X-bar chart as the second data point on the chart. Similarly, for each of the means and the other samples, we will get the respective points on the chart. The average of all these means is plotted as the center line for the control chart. And it will be 3 standard deviation above and under this center line that will determine the control charts, the control limits. Similarly, we can look at the range chart, which depicts the range of the 5 samples that were taken. So if we're looking at the second order observation, the minimum is 21.45, the maximum is 24.34, therefore the range is 2.89, and that is the point that is depicted on the R chart. The average of all of these ranges for all the samples is plotted as the center line, and in this case it is 1.997. And this value is called the XR bar. So the mean of the X bar chart is called X bar bar, and the mean of the range chart is called R bar. We can then use both control charts to learn about variation in the process. In this case, all points in both charts are within the control limits, which indicates that the variation in the process is due to common variation and not special cause of variation. If this common and natural variation is not meeting customers' expectation, then management needs to address this issue by redesigning the process of the product, investing in technology, or any other action that can reduce the existing common variation. If there's a single group of observations that is a higher mean than the rest of the groups, then it indicates that during the particular time, the process was out of control. This signals to the operators of the process that they should take action and reduce the special cause of variation, say by maybe recalibrating the machine. If there's a single group observation that is a higher range than the rest, then that might indicate that there was an outlier that pulled the range of the 5 samples to be higher than the rest. Again, the operators of the process can use this signal to determine the special cause of variation and address it. In this case, it seems that the first signals that the mean is gradually getting higher were not addressed right here. The upward trend on the X-bar chart clearly indicates that the operator of the process needs to determine what is causing the process to produce higher measures and to take corrective action to reduce the special cause of variation and bring the process to be stable and under control. To summarize, the X-bar or the mean chart provides information about the central tendency of the process, and it signals any changes in the averages across the samples. The R chart, or the range chart, measures the spread within each sample. If the process is stable and in control with no special cause of variation, then there's 99.73% probability that all points will fall in between the control limits on both the X-bar and the R chart. However, neither chart on its own is sufficient to determine if the process is in control. We need to examine both charts, the spread and the mean, to assure that the process is in control. If the process is in control, then all variation is due to common variation and there's no special cause of variation. One thing we need to think about is how to choose the subgroups. Those are the subgroups that are chosen so that the sample within each subgroup is going to be homogeneous. In the other case, we were looking at samples of 5. The subgroup size was 5. We want to assure that there's minimal variation within the subgroup. So therefore, we will look at things that are homogeneous, like the same operator, the same shift, particular days, machine, plants, suppliers, material types, and so forth. By minimizing the variation within the subgroup, it will be easier to detect special cause of variation that affect the averages between the subgroups. Once we have control limits, we should not change them. There shouldn't be a reason to change them unless there is a change in a process design. We purchase, for example, new equipment. There's a significant change in material. In other words, as long as there's nothing common, natural change in the process, we will not change the control limits. If we do, then we will have, if we're changing the control limits every time, the conclusions we will have will not be reliable. Quickly, just to remind you that there are different types of data. So for variable data that is on a continuous scale, like we did before, weight, electrical current, time, cost, and so forth, there are a few charts that can be used. We will be focusing on the X-bar R chart in one of the optional tasks, and then I think the appendix in the reading from Harvard. There is a discussion about a little bit about attribute data. This is data that can be counted. For example, do we have a defect or we don't? Do we have a pass-fail, yes, no decision? Basically like binary variables or counting of variables. And we have about 4 different charts. The reading talks about the P chart and the C chart, but we will not focus on that. We will focus on the X-bar R chart just to get an idea about how the control charts work. And if you're interested, you can always go and further look at them. There's also a flow chart to figure out how to use which control chart is to be used for a particular type of data, set of data. But in general, if you're using something like the control chart builder or something in JAMP, they will give you good advice of what to use, which will probably be the best fit for the data, although you can also change that as needed. So one more thing before we finish, just to summarize everything. When we have a data set, we need to, we have a process. We need to choose which variable, whether it's variable or attribute measurements we want to look at, determine the basis, the size, and the frequency of the sampling. We prepare the data, we record the data, we collect it, and we obtain relevant statistics, we do some charts, we obtain a control chart and analyze it as needed. And this can all be done using some software. And then once we figure out how we get the process in control, we just use the control charts, the same control limit, to continually plot the data so that if the process gets out of control, the operator of the process can take action, identify what's the problem, and make necessary adjustments. We also have to remember that rather than controlling just key output quality characteristics, we should control everything from every input that comes in. This requires, because if we have bad output from these, then the input for this process obviously is going to be problematic. So for example, if we have something that is wrong coming from the supplier, our raw material has a problem, then that can be the cause of the defects that we're having. So understanding the relationship between inputs and outputs, developing that during designs, getting input from customers, engineers, suppliers, and so forth is an important aspect of planning for quality control. So in general, to reduce variation, which is what we want, we use control charts. And this is what we call the voice of the process. We get special signals for special causes of variation, and we correct them. Once the process is in control, we know that any variation is due to common variation that is inherent to the process. And in this case, we're going to conduct capability analysis, which is basically capturing the voice of the customer and understand how the process matches up with the requirement for the customers and signals any possible need to address common cause of variation that needs to be done through redesign of the process, something more than just the special cause of variation that we needed to address. Looking at capability analysis is going to be the topic of the next video. Thank you.